It doesn't really matter.
All right, let's get started. Just some announcements. The Chapter 6 Achieve will be posted later today. And then that's due as usual next Monday at 9 a.m. I have my usual office hour today at 1. And then Wednesday, my office hour is at 2. I will let you know every week, but it won't be uncommon that my Wednesday office hour has to change. Sometimes it'll be 1, sometimes it'll be 2. But again, I'll let you know every week when it will be. I'm just on a new committee, and we're meeting some weeks at 1 p.m. on Wednesday. So those are the weeks I'll have to move it. And that's all for today for announcements. So we're going to go ahead and start our next chapter, which is Chapter 6. Chapter 6 is all about thermochemistry. And really, this chapter is about energy, the energetics of chemical reactions, how we can calculate energy changes, and what that looks like. So, sections here as an overview, list of learning outcomes as an overview, but we'll jump right in to section 6.1. So, the first few sections of this chapter are setting up the calculations and problems that we'll solve towards the end of the chapter. So background information for a couple of sections, and then things will get exciting. But this unit or this section, we are just defining energy and then talking about units that we use to communicate energy. So energy is the ability to do work or to transfer heat. And then work is defined as the displacement of an object against an opposing force. So we'll talk about work in a little bit more detail, talk about energy in more detail. But on this slide we have types of energy, and really the two overarching types of energy are kinetic energy. That's the energy of moving objects. So anything moving has kinetic energy. We can think at a macro scale of things that are moving, like we're walking around, we have kinetic energy. Planes flying, they have kinetic energy. We can also think of molecules in a system. So in the air in this room, we have oxygen gas. Those molecules are moving around. They have kinetic energy. In a saltwater solution, the salt particles or the ions are moving around. Water molecules are moving around. And then even in a solid, those particles have some kinetic energy. It's a lot lower kinetic energy than liquids and gases, but unless we're at absolute zero, then the particles have kinetic energy. And then the other overarching type of energy is potential energy. This is energy that is stored. On the slide for potential energy, I'll talk more or give you all some more details about that. And then thermal energy is energy of a hot object, so we can feel heat, transfer heat. And then radiant energy is energy content of electromagnetic radiation, for example, visible light. But let's first focus on kinetic energy. So every moving object has kinetic energy. So we kind of already went through some examples. Molecules are moving, they have kinetic energy. Atoms are moving, they have kinetic energy. Electrons are moving, electrons have kinetic energy. Jets have kinetic energy. This is our formula for kinetic energy of an object, where m is mass and v is velocity. And the unit for energy that we use in chemistry is most commonly the joule, which is 1 kilogram meter squared per second squared. So kilogram is our unit of mass, or unit for mass, And then velocity is meters per second. So if we square velocity, we have meters squared per second squared. So for any moving object, if we know the mass and the speed, the velocity at which it's moving, then we can calculate its kinetic energy with this equation. Potential energy, we won't necessarily calculate, but we've defined this as stored energy, an energy that's related to position. So in this image here, we have a skateboarder. When the skateboarder is at the top of the half pipe, so this far left image here, if you can imagine a skateboarder out there, they might not be moving, so they don't have kinetic energy, but they have a high potential energy because they're at a position at which if they lean forward or move forward, then they're going to gain a lot of kinetic energy. So that stored energy up here related, or potential energy is related to position. Being in that position, you have stored energy, and we call that potential energy. Then as the skateboarder moves down the half pipe, they've increased kinetic energy, they're moving faster, and they're decreasing potential energy because now they're no longer at that high position where they can gain more kinetic energy. So at the low point, they have low potential energy. There's nowhere for them to fall forward, but they have high kinetic energy because they're moving fast. And then as they go back up the other side of the half pipe, they've slowed down, so decreasing kinetic energy, but they're at a higher position where they could fall and gain kinetic energy, and so that's higher potential energy. So this is a macro example of potential energy and converting that between potential and kinetic. Here are two more examples of where we can compare amounts of potential energy. We can think about it in terms of gravity. So gravitational potential energy is just like that skateboarder example. When a backpack is on the table, it has higher potential energy than when it's on the ground, because when it's on the table, it could fall and then be positioned on the ground. And that's related to gravity. We can also think about potential energy in terms of electrical energy. So if we think about a hydrogen atom, so we have a proton in the nucleus, and then an electron somewhere in the electron cloud. When the proton and electron are in that atomic shape, the electron is orbiting the nucleus, the proton. That's a lower potential energy state. If we separate the electron and the proton, so we have something that's negatively charged away from something that's positively charged, they have high potential energy. So we have this arrow here showing increasing potential energy toward the top. High potential energy because if we have a negative and positive, if they get near each other, they're going to then exist in the atomic shape where the electron is orbiting the nucleus, the proton. And this is a lower energy state than compared to when they are separated, when they're a free electron and proton. Okay, so little summary of kinetic and potential energy. And then when we are communicating about energy in science, we already said this, but we use the joule or J. And the joule is 1 kilogram meter squared per second squared. So that dash line is missing there. Make sure you add that to your notes. Second squared should be in the denominator. So we talked about joule. That is a common unit for chemistry. The calorie is another common unit, lowercase c, or CAL for short. Later in the chapter, we're going to learn about calorimeters. So that is a apparatus we can use to measure heat exchange in a sample. that method is how the calorie was defined. We'll talk about that in more detail later, the calorimeter, but the calorie, 1 calorie, is the amount of energy needed to raise the temperature of exactly 1 gram of water by exactly 1 degree Celsius. So the amount of energy required to do that is defined as 1 calorie. And then this is a conversion, unit conversion here. If you need to convert between calories and joules, you can use this unit conversion. 1 calorie is 4.184 joules. And that brings us to the end of the first section. So really just getting some reminders of what energy is, foundational concepts, to move on to section 6.2. But before we do that, are there any questions? Okay. Then 6.2, we're going to continue talking about energy, but also talk about heat and work and their relationship to energy. So one thing that is important to define is this law of conservation of energy. You might remember from this example, the skateboarder has high potential energy at the top of the half pipe. Its potential energy is converted to kinetic energy. So they're moving faster, and then kinetic energy is converted to potential. So in this example and in life, energy is never created or destroyed. It can change forms or it can be transferred between objects. So in this example, the potential energy was converted to kinetic energy, which is converted back to potential. So energy is never created or destroyed in any process, but it can be transferred from one object to another, or it can be transformed from one form of energy into another. So energy is conserved. In an earlier chapter, we talked about the law of conservation of mass. So same idea, mass cannot be created or matter cannot be created or destroyed. Energy cannot be created or destroyed. This next slide shows this energy. Well, okay, here we have energy being transformed from one form to another. The next slide shows energy being transferred from one object to another. So if you play pool and you hit the cue ball into a collection of other pool balls, the cue ball has energy. You're giving it kinetic energy. It's moving toward the stationary other pool balls. And then this cue ball will transfer energy to the other objects here. And the energy is transferred to these other pool balls and then they can move around. So this is energy being transferred from one object to another object. When we perform chemical reactions or chemical transformations, they will require energy. So energy from the surroundings is then transferred to that reaction, or the reaction will release energy. So energy from the reaction will be transferred to the surroundings. And that's really the baseline understanding of what thermodynamics is. So thermodynamics is the quantitative study of energy transfers and transformations. And so we will talk about the system. So the thermodynamic system is what we want to describe and study. So if we're talking about some chemical transformation, that transformation occurring would be the system. And then everything else is described as the surroundings. And based on the law of conservation of energy, the energy cannot be created or destroyed. Any energy that's lost by the system to the surroundings, or any energy that's lost by the system is gained by the surroundings, or any energy that's lost by the surrounding is gained by the system. And so that means we can use this equation here, this statement that of all energy in the universe, this will never change. This is always constant. And this is equal to energies in any system plus the energy of all of the surroundings. So we can use this, and we will use this in some calculations. The internal energy of a system is the sum of all kinetic energy, so energy of movement, and all potential energy, so energy of position. Sometimes and you'll see this in your homework, is E. So in the achieved questions, they say, I think they're asked for E, and then they note sometimes internal energy is represented as U. Either way is fine. So this image up here in that top right corner, we have the system which would be the system that we're studying. That's just represented as a purple block. So we're assuming some energy transfer is occurring between the system and its surroundings. So the green and purple arrows are indicating there's a energy transfer. We'll talk about if we have an open system, then mass can be transferred as well between the system and the surroundings. But any energy that's lost by the system would be gained by the surroundings, or any energy gained by the system would be taken from the surroundings. So our next slide here, just describing 3 types of systems. So an open system would be a system where both matter and energy can move between the system and the surroundings. So an example you might be familiar with is fireplace, burning wood in a fireplace. Burning wood is a combustion reaction, so we're burning the carbon molecules in wood with oxygen in the atmosphere that produces carbon dioxide, which is then lost to the surroundings. That's a gas that's released to the surroundings. So that is a matter. That is matter that's lost to the surroundings. Oxygen is being gained by the system from the surroundings, and then also energy, the heat that we feel, is being lost from the system to the surroundings. So matter and energy can move between the system and the surroundings. That's an open system. A closed system is when energy can move between the system and the surroundings, but matter cannot. So an example is a pressure cooker. You have a lid on your pressure cooker. Now, no matter is being released to the surroundings or brought in from the surroundings, or this flask here with the stopper, none of the mass from inside the flask can be released to the surroundings, and nothing from the surroundings can go into the flask where the reaction is taking place. So that's a closed system, and then an isolated system, which in reality is really difficult to achieve. It requires pretty expensive materials and expensive materials. This is where neither matter nor energy can leave the entire system. A thermos that works perfectly is an example of a isolated system. A lot of thermoses do transfer heat between the system and the surroundings, but if you can imagine a thermos that works perfectly, absolutely no heat is transferred, that would be an example of an isolated system. Yeah.
So how would a closed system transfer energy?
Oh, okay, good question. Yeah, we can. Okay, here's an example. Well, I'll have a more detailed example in a couple of slides, but an example would be if you're doing a reaction that releases heat, and you hold the flask, you'd be able to feel that heat from outside the flask. So it's transferring energy through the material of its container to the surroundings. Good question. Okay, a little bit more about work and heat. So work is energy that results from a force acting on an object over a distance, and then heat, which we represent as lowercase q. This is the energy transferred between a system and its surroundings that causes a temperature change. So heat flow is a change in energy that's measured in joules. We've talked about joules. And chemical reactions frequently result in heat flows. So a reaction may release energy to its surroundings. This is exothermic. That term for that type of reaction is an exothermic reaction. Thermal heat energy is exiting the system, exothermic. A reaction that requires energy that can be supplied by its surroundings is an endothermic reaction. Okay. So here we have two visualizations of an endothermic reaction and an exothermic reaction. An endothermic reaction, which we have here on the left, is an energy absorbing reaction. So energy or heat from the surroundings, that lowercase q, is being absorbed by that reaction. So an example of this, you may have experienced this, but if not, I'll try to describe it as much as I can. There are some ice packs that you can purchase that are not frozen water. There are different chemicals within the ice pack, and you have to like crack the ice pack and move the particles around in order for the ice pack to get cold. So when you're cracking the contents within the ice pack, within the outer ice pack, that's releasing chemicals that undergo a chemical reaction. That chemical reaction is an endothermic reaction that requires a lot of energy. And so having that reaction occur within the ice pack takes a lot of energy from the surroundings being the outside of the ice pack. And so we on the outside can feel the cold from the ice pack because the reaction within the ice pack is endothermic and is taking in energy. So the surroundings would be outside the ice pack. This would lose heat, this would lose energy because the system is taking in energy from the surroundings. So that's an endothermic reaction. An exothermic reaction is where we have a reaction that is releasing energy. An example of this would be combustion. So we're releasing energy, we feel the heat. That's why we use a bonfire to stay warm when it's cold out, or a fireplace to keep warm inside. That reaction produces heat, and so that's an exothermic reaction. Now the internal energy of the system, that change in internal energy when a reaction occurs, so we use delta to indicate change. Change in internal energy is equal to the energy at the end of whatever reaction is occurring minus the internal energy at the beginning. This is the change. We can also calculate internal energy as the heat exchange plus the work exchange. Now, if we have heat being absorbed by the system or released by the system, that changes the sign of Q. And then same thing with work. If work is being done by the system, we have a certain sign for Q. If it's being done onto the system, we have a certain sign. So the next slide just summarizes all of these signs. So we'll start with heat first, Q. If a system is gaining heat from the surroundings, the system is increasing in heat and thermal energy, then Q is positive. If the system is giving away heat, if the system is losing heat, then we say Q is negative. So if you're given a statement that says a system or a reaction occurred that required 5 joules of energy from its surroundings, then that system's Q value is positive because that system had absorbed energy from the surroundings. For work, if work is being done by the surroundings onto the system, it's a positive sign for work. If the system is doing the work, then it is a positive sign. So, if the system overall is gaining internal energy, then we have a positive sign for delta U. If it's losing internal energy, then we have a negative sign. So let's do this learning check here. Before I start the iClicker, let's think about what's going on. So we have a chemical reaction performed in a flask that's connected to a piston. So we have a closed system, and the piston prevents anything from escaping in that area. The reaction releases 920 joules of heat to the surroundings, and the gas produced performs 530 joules of work on the surroundings, and we see that by the piston being pushed upwards. So, question is, what is delta U for this reaction? The iClicker, none of the questions are actually calculating delta U, but just setting up doing that calculation. So, what's the value for the for work, for heat, and then equation that we'll use? So I'll get this started. We'll spend a few minutes here. Oops.
Comments around that. So it's not going to the first one.
They asked, I did.
Let's have one more minute. Okay, I think that's everybody, so I'll stop it here. Okay, great. A mix for all of them. I love a mix. So let's think about what's happening. It says a reaction is releasing 920 joules of heat. The reaction is our system that's releasing 920 joules of heat. This means this is an exothermic reaction. Heat is being released. And so that means for Q, our value is negative. When the system loses heat, we have a negative value for Q. So Q is negative 920 joules. In this reaction, a gas is produced. So this is one of a reaction type where the product is a gas. That gas that's produced is performing 530 joules of work on the surroundings by pushing the piston upward. So it tells us 530 joules of work is done on the surroundings. That means the system is doing the work. So if the system is doing the work, then our W value is also negative. So negative 530 joules. So in this problem, we're given Q, we're given W, so we can calculate delta U, the change in internal energy, using our equation Q plus W. The other equation, U final minus U initial, that will give you delta U, but we don't have those values. We don't have the initial internal energy of the system and the final internal energy of the system. So we'll use Q plus W, so negative 920 joules plus negative 530 joules. And this was, I don't remember, 14 something? Yeah, 1450? Thank you. Negative 1,450 joules. So that's our delta U value, the change in internal energy. Yes.
So it's negative just because the work is on the surrounding, not on the system.
Right. Yeah, the work is done by the system on the surroundings. If the work is done by the surroundings to the system, then it would be positive. Yeah. Other questions on this? Okay. Being more and more detailed for understanding of energy. So energy is defined as a state function, and we'll talk about what that means in this section, and that will come into play when we do some calculations. So state functions are properties that depend only on the conditions that describe them, not on the pathway to obtain certain conditions. So an example of a state function unrelated to chemistry is a change in altitude. So this image shows 3 family members, a father, mother, and a daughter that are all going from San Francisco to Denver. The daughter drives to LA and then flies to Denver. The father takes a train straight to Denver, and the mother flies to Dallas and then to Denver. Okay, so they all took 3 different paths to get from San Francisco to Denver. No matter what the paths are, the statement here is that the change in altitude between San Francisco and Denver is the same no matter what path you took. So that change in altitude is a state function. You could find the change in the state function can be measured using the most convenient method. So if you're trying to find the change in altitude between San Francisco and Denver, you could take the mother's route and see the change in altitude between San Francisco and Dallas, and then the change in altitude between Dallas and Denver. Or you could take the daughter's route, but really the most convenient method is to see the change in altitude from the father's starting position to the very end. And it doesn't matter, that would be the change in altitude for all 3 people. So the change in altitude between San Francisco and Denver is the same no matter the path. And then path functions, so these are functions that are properties that depend on how the change occurs. So the distance between San Francisco and Denver, it's not really the distance between, but the distance traveled between San Francisco and Denver depends on the route taken. So all 3 family members are traveling a different total distance because they're taking different routes. So distance is a path function. Work is a path function, and heat is a path function. But internal energy is not. So here's an example more closely related to chemistry. So liquid ethanol, which is shown at 25 degrees Celsius in this beaker, has a specific internal energy. We're just giving it the letter capital U with a subscript liquid for liquid ethanol. This liquid ethanol can be formed by melting solid ethanol, so starting at the solid, melting to the liquid, or taking gaseous methanol and condensing it. In either case, the internal energy of the liquid ethanol is the same. So the internal energy, whether you're starting with a solid or starting with a gas, the internal energy of the liquid is the same. So not delta U, but U is a state function. But we said heat and work are not state functions. So the heat that's required to warm up the solid methanol or ethanol to produce the liquid is different than the heat required that needs to be released for gaseous or vapor methanol to form the liquid. Okay, so we'll use this idea that internal energy is a state function in our future equations. We're ready to go to 6.4, where we are going to talk about energy and enthalpy. So enthalpy is more commonly reported for chemical reactions. So we'll talk about enthalpy change. And then we'll talk about pressure, volume, work, and that's actually what we'll talk about first, is this pressure, volume, work. So pressure, volume, work is work done when there is a volume change measured against an external pressure, and that external pressure remains constant. So the work that is done, W. Pressure, which we represent as capital P, and the change in volume are related in this equation here. So W work is equal to the negative external pressure times the change in volume. Our change in volume is final minus initial, final volume minus initial volume. And then pressure is often reported in units of atmospheres. So work is often reported in joules, which is kilograms times meters squared per second squared. But pressure is usually ATM, atmospheres, and volume is usually liters. So atmospheres times liter does not give us a joule. So when going through these equations, you will often need this unit conversion. Or if you're trying to calculate work and you know the change in volume, you know the external pressure, you can multiply them together and your unit will be liters times atmospheres. You can convert that to joules by using this unit conversion. So again, this is an example, the question that we had looked at previously, where we have a closed system, we're assuming a constant pressure outside of the system. This is our reaction. We're mixing an aqueous compound with a solid compound, and this reaction produces a gas. So that's the gas that's released in the reaction that does work on the piston. And then we have water and another aqueous compound. With a constant pressure on the outside of the system, on the piston, any increase in volume will raise that piston. So this next question we'll go through here, this learning check. We have a chemical reaction performed in a flask, sealed with a piston, same thing as the last image. We have the initial volume of the system, the final volume, and we have a constant pressure of 1 atmosphere. And we are calculating the amount of work performed during this reaction. I'll give you all, let's say, 2 minutes. It's not an iClicker, I just want to give you all a couple minutes to start it, and then we'll go through it together. Okay, we'll start going through this one together. So We are calculating the amount of work performed in joules. We are given a pressure and we're given change in, well, we're given two different volumes. So we can calculate change in volumes. So we will use work is equal to negative pressure times change in volume. So here's the equation that we'll use. Let's first calculate change in volume. So that's the final volume minus initial. Whenever we're calculating change, we'll start with the final and then subtract the initial. So change in volume, final volume, which is 0.375 liters, minus initial volume, 0.550 liters. So that gives us a change in volume of negative 0.175 liters. So we end with a smaller volume than we started, so our change in volume is negative. So we're given pressure. We have 1.00 atmospheres as our pressure. And then we just calculated change in volume, negative 0.175 liters. So we can calculate work using that equation there, and we get 0.175 liters times atmosphere, or atmosphere times liter, however you want to write it, is fine. So this is the amount of work done, but we're asked for the work performed in joules. So we need to convert this amount of work, which is in the units of liters times atmosphere, to units of joules. So work 0.175 liters times atmospheres times our conversion, which is 1 liter times atmosphere is equal to 101.325 joules. So we cancel out liters times atmosphere and we get 17.7 joules of work. Questions on this problem here? Okay, so how about, not part A, second part B. Is the piston going to move upward or downward? What do you think? Upward? Others? Down? Up? Okay, we got a mix. So what are some things that we should look at if we're thinking about if it's going to go up or down? The volume. We could also think of the work. So work is positive, which means the surrounding is doing system on the work, or on the surroundings is doing work on the system. And we're decreasing in volume. So if we're decreasing in total volume, then the piston should be going downward. So it is downward. And if we go back to that image here, this is not what's happening, so not the position, but if we just look at one of these, we're decreasing total volume, the piston's going to go down. And we're not doing work on the surroundings, where the surrounding is doing work on the system, so that also indicates that the piston will go downward. Okay, we will end here for today. We'll start talking more about enthalpy on Wednesday.